Well, the British Museum have asked me here today to date this Egyptian mummy. It's of a priestess who lived and died in Thebes, they think about 1000 BC. And they believe this because of the style of decoration on the sarcophagus and the way that the mummy's actually been wrapped. And the technique I'm actually going to be using is radiocarbon dating.
All living things contain 3 types of carbon atom. They are chemically identical, but their total mass is different. They are isotopes of carbon. 99% of carbon atoms have 12 particles in their nucleus. This is their mass number. They have 6 protons and 6 neutrons. But there are other kinds of carbon atoms. 1% of carbon atoms have a mass number of 13. They've still got 6 protons, but instead of 6 neutrons, they have 7. And finally, 1 in a million carbon atoms is radioactive. This means that their nucleus is unstable. The mass number of these radioactive atoms is 14. Again, they have 6 protons, but these unstable atoms have 8 neutrons. Excess neutrons make the nucleus break up. It emits radiation and changes to form a nitrogen nucleus. It's these radioactive carbon atoms that are used in the carbon dating of the mummy wrapping.
So what I'm here to do today is just to remove a small sample from the actual wrapping, and I noticed there's a small piece of it that's come very loose, it's almost off, so I'm actually just here to remove it with my scalpel and take it away to Oxford for analysis. And there it comes.
Cosmic rays from outer space are constantly bombarding the Earth. Occasionally they collide with a nitrogen atom in the atmosphere to form carbon-14. The carbon-14 immediately combines with oxygen to form carbon dioxide. This radioactive carbon dioxide finds its way into plants. Plants are eaten by animals and humans.
Well, radiocarbon dating is applicable to anything organic, anything that's lived really between about 200 years ago and less than about 50,000 years ago. And the principle is fairly simple. Anything that's living or once lived exchanges carbon with the atmosphere. And of course, when the organism dies, that exchange ceases. And of course, that applies just as much to the plants that have gone to produce this textile, so that's where this is particularly relevant. And another material that's particularly susceptible to radiocarbon dating is, of course, bone. Bone is constructed of collagen, of protein, and it's that protein that contains the carbon. And this is one we have here from a medieval leper, from a cemetery, a leper cemetery in East Anglia, which again falls into the range of radiocarbon dating.
The amount of carbon-14 in a dead body is less than in a living body. This is because radioactive carbon-14 is decaying and isn't being replaced. Scientists have calculated that it takes 5,700 years for carbon-14 to decay by half. This is called the half-life of carbon-14. It would take another 5,700 years for it to decay by half again, and again, and again. If we plot the half-life as a graph, with the amount of carbon-14 on the vertical axis and time on the horizontal axis, it will look like this. Using the half-life graph, scientists can carbon date the mummy, but first the mummy wrapping must be cleaned.
We just need to get rid of all the pieces of dust and so on, so we've eliminated everything except the actual cellulose that the wrapping is actually made from. Hi Jill.
Hello.
Here's the sample, it's over to you.
Okay, thank you.
Yeah.
A small sample of mummy wrapping is placed in a combustion chamber, where it is burnt and converted into carbon dioxide gas. The gas is sealed in a glass tube. All the carbon atoms from the wrapping, including the radioactive ones, are now trapped in this tube.
Well, our sample of mummy wrapping has now been reduced to an ampule of CO2 gas, which I'm actually going to inject into the machine. And this is where we actually insert that ampule, and what we want to be careful about is that we don't introduce any contaminating carbon. So we put it in this sealed tube, and then we simply wobble it to break the ampule and release that gas into the system.
This machine is called a mass spectrometer. It uses powerful magnetic fields to sort out and measure carbon-12, carbon-13 and carbon-14.
Now, what the mass spectrometer has actually done is measured directly the amounts, counted the amounts of C14, 13 and 12 in the sample. And here it is just come up on the screen. This is the one we're concerned with. And you can see the mummy wrapping here has 69% of its original carbon left. In other words, it's lost about 31% of the carbon it would have had in life. And from this, the computer's worked out that its actual age in radiocarbon years ago is 2,940.
The computer has calculated that there is only 69% of the original radioactive carbon-14 left in the mummy. That corresponds with the yellow line on the graph, which gives us the time of burial as 2,940 years ago. There are three types of radiation. They're called alpha, beta and gamma. Alpha particles consist of 2 protons and 2 neutrons. Beta particles are fast-moving electrons, while gamma rays are electromagnetic radiation, similar to X-rays. This radioactive disk emits alpha particles. They're detected by a Geiger counter. Alpha particles don't travel very far in air. Beta particles travel further. And gamma rays travel further still. Alpha particles are easily stopped by a piece of paper. Beta particles are stopped by a thin sheet of aluminium. But gamma rays are only stopped by a thick piece of lead. These are the alpha particles. They have a large mass and are relatively slow. They're stopped easily by thin materials. Beta particles are much smaller and move at higher speeds. Therefore they pass through thin paper, but they can be stopped by thicker materials. Gamma radiation consists of high-energy waves rather than particles. This radiation can only be stopped by very thick, dense materials, like lead. Radioactive substances that emit gamma rays, like technetium, can be injected into the body to produce images. This machine has a gamma camera. It detects the gamma rays emitted by the technetium. 15-year-old Daniel was born with a hole in the heart. He's been coming to Guy's Hospital in London since he was 2. Today, he's here for a technetium injection. Radioactive technetium is pretty dangerous stuff, but a small measured amount of it can detect a life-threatening medical condition. For Daniel, radioactive imaging is the best way to make sure his heart is functioning correctly. But first, Daniel's technetium injection has to be made up in the hot lab. Safety clothes and radiation monitors have to be worn to protect the staff.
This is where the radioactive technetium is produced, and this is what we're going to use to make up Daniel's kit this afternoon. I'm going to use a syringe and needle to draw up the radioactive technetium, but to protect myself from the gamma rays, I'm going to insert it inside a lead syringe shield, and at the front you can see there is lead glass so that I can see through into the syringe what I'm actually drawing up. The radioactive kit is now ready to be taken out and used to inject Daniel.
The technetium is taken to the preparation room, where the exact dose is carefully measured. The dose is small enough to create a good image of Daniel's heart, without putting him at too much risk from the dangerous effects of radiation.
I now have my dose. I'll take it to the camera in this protected lead box. Daniel.
We're just going to get you ready for the scan now, Daniel. If you turn your head round that way, we're going to move the camera down. It's going to be very close to your chest, alright? But it won't move once it's in the right position. Okay? In a minute, Penny's going to give you the injection, and you've got to keep still for about 5 minutes. Okay? The camera's going to be detecting the gamma rays so that we can take pictures of your heart.
As the technetium is injected into Daniel's arm, we can see it being taken up by the bloodstream, which will finally make its way to his heart. Radioactive imaging has many advantages over X-rays. A standard X-ray only produces a static image, but radioactive images enable scientists to see body functions such as blood flow and even bone growth. Here we can see gamma images of 2 kidneys. They have revealed that one kidney is actually larger than the other. There are other types of radioactive substances used in imaging, like radiofluorine. Again, a gamma camera is used to detect the gamma rays emitted by radiofluorine. Here we have an X-ray and a radioactive image of the same hand. On the left there's the standard X-ray, but it was the radioactive image that detected the non-cancerous growth. That's it today for Daniel. His heart has checked out fine, and was it an awful experience?
Didn't feel a thing.
For 30-year-old Stella, the results of medical tests were to change her life. At 29, she was diagnosed as having cancer of the cervix. Ironically, Stella owes her life to radiation, which can be deadly.
Well, they first detected the cancer because at this visit to the GP they did a smear test, and unfortunately that came back positive. And they then asked me to go to the hospital, where they actually realised through various other tests that it definitely was a cancer of the cervix.
Stella had a cancer of the cervix, which was a cancer which needs to be treated by radiotherapy. When we talk about cancer, we're talking about the uncontrolled growth of cells. Normally, there is a good balance between cells being generated and growing and cells being lost and dying. But in cancer, what happens is that balance becomes deranged, and instead we get more and more cells growing, and they form a lump. Radiotherapy damages all cells. It damages the nucleus of the cells and stops them dividing. But it damages cancer cells in a way that they cannot repair, whilst normal cells are able to repair the damage. So that over a period of time, you can kill off the cancer cells whilst leaving the normal cells healthy.
The first part of my treatment was a series of 28 sessions on a machine at the hospital which is called the Linac accelerator, and that sends out very high dosage of X-rays, which is part of the radiotherapy treatment. And I lay down on a bed under a big machine, and the machine actually sends out these X-rays.
And those high-energy X-rays are directed at the cancer, which is at the centre of the pelvis, and at the lymph nodes, which are at the side of the pelvis here. This high-energy X-ray treatment from the Linac accelerator is at about 100 times the energy of the X-rays that we use to take an ordinary X-ray picture, as you would have of your chest, and the dose which we deliver to the tumour is about 100,000 times the dose which we would use to take an ordinary picture. The only difference between X-rays and gamma rays is where they come from. Gamma rays come from the nuclear decay in a radioisotope, whereas X-rays come from a machine which works at very, very high voltages, often in the range of millions of volts.
The second part of Stella's radiotherapy was her internal treatment.
What I'm going to do is I'm going to use a bit of anaesthetic down below so that you don't feel anything, and then I'm going to slide this tube here through the cervix and into the uterus and connect you to the treatment machine, which will put the radioactive isotope into the applicators. So I'll see you in a few minutes when the treatment's over.
Whilst the treatment's going on, you'll hear various clicks and whirs from the machine. Don't worry about those.
Okay.
And there's also a continuous bleeping noise, which is the gamma monitor.
Right, okay.
All right?
Yeah.
At the end of 12 minutes, we'll come back.
Okay.
Last out.
Well, the radiation doesn't just stop inside Stella when she's having her treatment with the radioisotope. And if the staff who were treating her were to remain in the room, they would all get some radiation, even though it would be a small dose. Now, whilst it's reasonable for Stella to receive some of that radiation because she has a cancer, which is a very serious risk to her, it is not reasonable for people who do not have cancer to be exposed to radiation.
So are you happy with the films, Dr. Blake?
Yes, I think that now we've done the insertion, we can see on these films that the tube is nicely within the uterus and that the applicators are at the top of the vagina. With the correct positioning, we can go ahead with the treatment now.
Ready to switch on?
Mm-hmm.
The radioactive source is put into these tubes by the machine in order to deliver the radiation in a concentrated form around this area here, which is where the cervix is sitting. And so that is the area that gets the biggest radiation dose, and therefore we're able to cure the cancer. Well, when we were talking about the risks and benefits with Stella, we had to cover a whole range of side effects that can occur with radiation. Side effects to the normal tissues in her pelvis, such as her bladder and her rectum. But we also had to talk to her about fertility as well. Another tissue in the pelvis is the ovary, and radiation will have an effect on that also.
The risk of having the treatment was that I knew from the beginning that it would leave me infertile. And so obviously, even though I'm recently married and I'm still quite young, I won't be able to have any children of my own. However, I would like to add to that had the cancer not been discovered, had I gone on to have some children with my husband, I may have left them with no mother. And so from that point of view, I have to say that it's better the way things have turned out. I'm still here, I'm healthy, I'm happy, I have a nice life with my husband, and I don't think I can say much more, really.